In this module, we will try to get an understanding of steady-state heat conduction, and then we will develop a mathematical expression to determine rate of heat transfer across a rectangular wall when you have steady-state heat transfer conditions. So recall from the earlier module on conduction, we were looking at an example of heat transfer through the wall of a house. Inside was considered to be warm, so the temperature is higher inside, and outside was colder, so the temperatures are lower outside. So the heat transfer is through this wall from inside to outside. So now if we assume that both the inside temperature and the outside temperature are constant, that means they are not changing with time, then if we were to plot the temperature profile, it will probably look something like this. This profile will not change because the inside temperature is constant, it's not changing, and the outside temperature is not changing. So under these conditions, we will say that the heat transfer through this wall is under steady state conditions. The temperature does not change with time, it only changes with location. So with that, we will then go ahead and try to develop a mathematical expression to tell us how much heat is transferring under steady state conditions. Remember, we talked about Fourier's law, and Fourier's law is written as Q equals minus Ka delta T over delta X. We will rewrite Fourier's law in differential form as Q equals minus Ka dt over dx. So note that this is in rectangular coordinates because we have a rectangular wall. So we will also write that Q, we will change that to Qx. We'll write a little subscript x to tell us that this is in rectangular coordinates. Now what we want to do is to solve this equation, and to solve a differential equation you certainly need the boundary conditions, and we need two boundary conditions here for temperature at a certain location. So if we have a coordinate system with x increasing from the inside of the wall to the outside, we can say that at x is equal to x1, temperature T equals T1, and at x is equal to x2, we will say that temperature T equals T2. So now we look at our differential equation, and again from your course in calculus, a very common procedure to solve these types of equations is by separating the variables. So in our case, there are two variables, the temperature and the location x. The thermal conductivity K is constant, area is constant, as well as the rate of heat transfer under steady state conditions is constant. So we will say Qx, and we will move this dx to the left hand side. So we have dx on left hand side, and by separating the variables we mean that x is on one side of the equation, and then temperature, our other variable, will be on the other side. So Qx dx equals minus Ka dt. Now we can go ahead and integrate this. So we will integrate x from x1 to x2. So on the left hand side we have an integral for dx, x1 to x2, and also we have an integral on the right hand side, t1 to t2. Note that I kept Qx out of the integral on left hand side and minus Ka outside the integral on the right hand side because they are constant terms. Now again, from calculus you will remember that the integral of dx is x. So we have qx and then x evaluated at limits x1 and x2. And on the other side we have minus ka. Again, the integral of dt is t, and again evaluated at t1 and t2. So we can go ahead and substitute the limits. So we have qx, and in parentheses we have x2 minus x1, and on the right hand side minus ka t2 minus t1. And so with that we can go ahead and rearrange some of their terms to get the rate of heat transfer qx, and we'll keep that on the left hand side. And on the right hand side of the equation we will have minus ka t2 minus t1, and we will take the quantity from the left hand side down to the denominator of right hand side, the quantity x2 minus x1. So our integrated equation now for steady state heat transfer is qx equals minus ka t2 minus t1 divided by x2 minus x1. Now note that x2 minus x1 is the thickness of the wall, and so what we will say is that x2 minus x1 equals L. We'll just use L for the thickness, and in the numerator note it's T2 minus T1, but remember heat is transferring from inside to outside. Temperature T2 is lower than temperature T1. So in the numerator then, if we rewrite our equation as qx equals minus ka, we can write that as, we can change the terms in the parentheses. We can say it's T1 minus T2, and that will change the negative sign. We bring the negative sign out of the parentheses, and that will cancel out with the outside negative sign, and we will have a positive value. And in the denominator we have L. So our final expression then is qx equals ka T1 minus T2 divided by L. Note that T1 temperature is higher, as we know, on the inside of the wall, and lower on the outside, T2. So this is now a very useful equation that we can use to find out the rate of heat transfer. Now at this point I would also like to introduce another concept. The concept is called thermal resistance concept. Now you would have taken a course in physics where you would have discussed that in an electrical circuit the electrical resistance can be described as electric potential divided by current. E was the electric potential, I is the current. So the analogy is that just like in an electric circuit, the current flows because of the electric potential, that in our case heat transfer, the heat is transferring because of the difference in temperatures. So as an analogy to electrical potential, we have the temperature difference. So the temperature difference in our case is T1 minus T2, and for electric current the analogy is the rate of heat transfer, Qx, and of course we have thermal resistance on the left hand side. We'll call it R thermal. Now we can go ahead and substitute here the quantity in the numerator for T1 minus T2. Remember that we just obtained an expression for steady state heat transfer as Qx equals Ka T1 minus T2 divided by L. So I can rearrange the terms here to move the T1 minus T2 keep that on one side and move all the other terms to the other side. So we will have T1 minus T2 equals QXL divided by KA. And if we go ahead now and substitute for T1 minus T2 in our expression for the resistance, for the thermal resistance, we will get, we will have QXL divided by KA, and then will be QX left over from the other expression. So in this case now, QX and QX will cancel out, and we will have L over Ka. So the thermal resistance is, under steady state conditions, equals L over Ka. And if you want to draw a circuit for heat transfer, we can say that we have temperature T1 on one side, and we have the resistance shown as thermal resistance, and then we have temperature T2 on the other side, and this thermal resistance is L over Ka. We will again consider this item when we are looking at more complex situations. But at this time, I would just like you to see how we obtain the equation for the thermal resistance that equals L over Ka.